I'm the Western Regional Manager for Heat Pipe. I've been in this position since July of about 2 years ago. My previous background was with wheels, so I have a little bit of experience with energy recovery systems. Today, in general, we're going to cover heat pipes for energy recovery and some of the applications and how to deal with those. First of all, brief outline. We'll talk about the role of energy recovery. We'll talk about HRMs and HRM-Vs in particular. We'll also talk about recovery efficiency ratio, and we'll also talk about some ways to enhance heat pipes and getting the most out of those systems and dealing with them on a regional level. So I'll refer to it a couple times. Select Plus is our design software. It allows you to do all the selections, performance, psychometrics, dimensional drawings. All the bin analysis is done within Select Plus. It's also cloud-based, so you can access it from anywhere. This information can also be shared back and forth between you, engineers, and customers quite easily. The big role of energy recovery, you have dealing with complying with local codes, but the big crux is reducing operating cost and reducing HVAC equipment size. What we're really the goal of energy recovery is to save money. There are added aspects of improving indoor air quality and getting LEED certified, but the real role of energy recovery is to save money. Now, ASHRAE standard 90.1 is really what pushes and drives a lot of what we do with energy recovery in the market today. With every iteration of 90.1, that threshold for outside air requirement keeps going down. So every time it's been re-released, that standard for outside keeps going down and down and down. So the need for energy recovery, not only to save money is a goal, but it's also to meet the standard of 90.1 as well. Now, there are some climatic variations for this, places where you can be excluded and take exceptions to 90.1. There are also exceptions you can take for labs and kitchens and toxic and corrosive fumes. And there's also one other exception, which we won't talk about in this arena. If a wraparound sensible air-to-air heat exchanger is used for dehumidification, and that's another aspect of heat pipes, which we could say for a later discussion you could take an exception to. There are 4 basic types of energy recovery systems. There are energy recovery wheels. There are fixed plate cross flow heat exchangers, Water-Glycol Systems or glycol loops, and then there are heat pipe heat exchangers. I'm going to talk about each one of these devices, give you some advantages and some disadvantages of all of them as well. So air-to-air heat exchangers or wheels in particular, they do sensible and latent recovery. They're 70+% effective, and they're very compact. They're very well accepted in the industry, probably the #1 seller of energy recovery devices in the industry today. One of the big considerations you have to take with wheel, though, is you have to bring those air streams together in order to accomplish that transfer. So they have to be right next to each other. There is a risk of cross-contamination with the wheel. You can never get down to 0%. You can get close, but you can't get down to 0. One of the big crutches you have for a wheel, though, it's a big moving part in the airstream. You have to maintain the belts. You have to maintain the bearings, seal shelf, and the motor. If you don't have a very good maintenance staff, wheels aren't going to be very effective and will fail pretty quickly. Depending on what type of wheel you have, you can have high static pressure, whether it's in laminar or turbulent flow, and you can have an issue with air leaks as well. One of the other critical things about wheels, typically wheels don't last the lifetime of the box that they're in. At some point in the lifetime of that box, you're going to have to replace that wheel. And I've seen that on numerous times. Fixed plate cross-flow heat exchangers, no cross-contamination of the airstream, 60 to 70% sensible effectiveness, and no moving parts. Now, there are some plates now that can do some latent transfer, but that latent transfer is typically in the 40% range, so it's not equal. One of the disadvantages is you're pretty limited in your design. You've got you can get some interesting air pass through an air handler. It's pretty difficult to clean a plate heat exchanger, and they take up a lot of space in the box. I ran an example recently. It took up 3 feet within the box, and I did the same with a heat pipe, and it only took up 1 foot. And as you know, with air handlers, real estate is money, so you can reduce the size of your air handler by switching heat exchangers. Another aspect of a plate is you have high static pressure unless you run lower face velocities. So that's another consideration. Water-Glycol loop systems, very advantageous for no cross-contamination and very flexible in design. These systems will allow you to run very long distances and be able to run, say, multiple exhaust and have single supply as well. One of the key disadvantages, it has very low effectiveness. You're typically in the 35% or less range. They have a low recovery efficiency ratio because of the energy required for the input. And most of those coils are very deep, so you have a high static pressure. One other issue which it needs to be pointed out is the controls of these systems. You've got pumps and motors, heat exchangers, a lot of parts and pieces in order to make sure those work very well. Heat pipes, very compact. You can have the airstreams side by side, or you could separate the airstreams and have two separated airstreams with some distance, and we'll discuss that a little bit further. There are no moving parts, so there's little maintenance involved. The maintenance you would see on a heat pipe is what you would typically see on any cooling coil that you would have. There's no cross-contamination risk, very durable, and a low static pressure. One of the big disadvantages is it's installation sensitive. You have to make sure it's level in order to ensure two-season recovery, and you're only 50 to 60% sensible effectiveness. Heat pipes, traditionally, what they'll do is heat will come in on this side over here. Heat will get absorbed, turn this refrigerant to a vapor. The vapor travels back over to the other side, and then it condenses and the liquid falls. It all happens within the same tube, very large tubes. One thing about this is typically, and with traditional heat pipes, you're looking 3/4 to 1 inch tubes, and you'll tilt it on one side to ensure that you have transfer from one side to the next. So, and the other thing is you have that vapor and liquid fighting for the same space within that tube. So it's not very effective, and a lot of times you'll have to have that tilt mechanism to make sure you get recovery at the right season. What we do is a little bit differently at heat pipe. Imagine two tubes stacked on top of each other, and they're circuited together. So heat would come in to this tube, turn this vapor to a liquid, this liquid to a vapor. The vapor travels up. Then on this side, it condenses, and the liquid falls. So you have this vapor and liquid chasing each other in a racetrack around this loop. We're able to use 1/2 inch tubes instead of the larger 3/4 or 1 inch. So we have less air pressure drop, and it's more effective by having those chase each other in a loop. We'll discuss what an HRM is. An HRM is a heat recovery module. It's designed for having adjacent airstreams. So you're going to have the airstreams right next to each other. These systems can be either unit or duct mounted. Here's an example of a side-by-side heat pipe in a winter condition. You have 75 degrees of inside air, 32 degrees outside air, and the supply air now, we've picked up 23 degrees. So we're 50 to 55% effectiveness with a 6-row, 500 feet per minute system. In a summertime condition on the same system, 75 degree inside, 95 degrees, we have a delta T of 13 degrees on this system. These systems, as far as airflow, we can have counterflow, which is the most productive, and then you can also have the airstreams in parallel flow. On a counterflow, that's the standard configuration. That performance is available within Select Plus, and like I said before, on a 6-row system, you're typically 55%. On a parallel system where it's a non-standard configuration, that performance would have to be done by one of our inside sales personnel or myself. That's typically 45% effectiveness, so you get about a 15 to 20% reduction in performance by going to a parallel flow on the airstreams. Now, you can have side-by-side arrangement for year-round, or you can do an over and under, which would allow you to only have single-season recovery. On a side-by-side, the heat pipes must be installed level within 1/8 of an inch from one side to the next. And like I said before, that can be calculated within Select Plus. This is an example of energy recovery heat pipes in the duct. And as you can see, we've got drain pans located in the duct just in case there's any condensate issues, typically on the exhaust side. And those would have to be by others as well. And then here's an example of energy recovery heat pipes within an air handler feeding the rest of the system. And over and under, you would only get single season recovery. On cooling recovery, the supply would be on the bottom. For heating recovery, you would see the exhaust on the bottom. You're going to have to make sure you've got drain pans if there's any condensate issues, and that performance can, again, be calculated in Select Plus. This is an example of an over and under. In this case, you can see the cooling. This would be for cooling recovery. We typically see more heating recovery over and under heat pipes than cooling recovery. How to control an HRM? Bypass dampers are typically used to control for economizer and frost control. We can have that as an option within Select Plus. We can select a bypass damper and do those calculations within Select Plus as well. If you need full control and be able to shut the system completely down, face and bypass dampers would be by others. Here's an example in North Dakota. It's an energy recovery system within, and it's got 18,000 CFM, 17,000 in the exhaust, and we saved about 2.6 million BTUs per year in this lab building. Some factors affecting the heat pipe performance. We use half-inch OD copper. We run from 1 to 8 rows. The face velocity, we have a maximum of 700 feet per minute within the selection software. And we run fin densities 9 to 14 fins per inch. And we can do those in copper or aluminum as well. We typically run 410A, but we can also run 134 as well. If you run 410A, we have a maximum temperature of 150 degrees and 200-inch maximum length for the entire length of the heat pipe. If we run a 134, we can go up to 200 degrees, but our maximum length for the heat pipe runs 150 inches. And within Select Plus, it'll give you set those parameters off as well. On the dimensional data, like I said, we can have up to 200 inches, and that's face area. That doesn't include any casing or anything like that. That would include the supply plus any gap that you would have in the middle for a center wall, or if you wanted to further separate that, we can go up to 8-inch gap in between those two systems, and then you would have to add in the exhaust side as well. The max face height is 60 inches per section. The max height that we would build a heat pipe to is up to 150 inches of face height, and that would be 3 50-inch sections, and they're self-supporting. After you get 150 inches, you'll have to have an intermediate support in the air handler to accommodate any extra weight. The width on a 1-row system is 6 inches. On a 8-row system is 13 inches, and all this kicks out of Select Plus when you do it. Quick summary of energy recovery heat pipes: very compact, very small. We're very flexible in the dimensions with the rows and fins. Another key factor of heat pipes is we're not stuck with a certain aspect ratio. You can be 2 foot high and 5 foot wide, or 5 foot high and 2 foot wide. It gives you a lot of flexibility. I've seen a lot of examples recently where we're running into some space issues within buildings, and they're putting the heat pipe in the duct that's running through interstitial space. So I've seen a lot of heat pipes recently in the ductwork, 2 foot high and 4 foot wide. We can foam the center a gap between to have further separation. Typically, heat pipe lasts 20 to 30 years. There's no cross-contamination risk. Most energy recovery heat pipes I've been applying them within colleges and universities for labs. I've also done a lot of hospitals and paint booths and some pharmaceuticals as well. It gives you an ideal situation for that. An HRM-V, that's the next version of an energy recovery heat pipe. It stands for vertical. It's designed for separated airstreams. So these airstreams don't necessarily have to be right in the same box. Those two can be unit or duct mounted. On a split level system, you would only get heating or cooling depending on which one's lower. On the same level, you could have the heat pipes do heating and cooling recovery. For single season recovery, if the exhaust is on the bottom, you would get winter recovery only. And if the exhaust is on top, you would get summer recovery only. Most that I've seen with these have been winter recovery, typically north of the Mason-Dixon line and out west. On single season, we can go up to 100 equivalent feet in the horizontal direction and up to 50 equivalent feet in the vertical. The max coil height is 30 inches, but you can have multiple stacks, and the max coil length is 155 inches. And this shows a typical circuit. As you can see, we've got a common header for the vapor and liquid lines, and the tubes run vertically and the fins run horizontally through this system. For year-round recovery, you must be level. Heat is transferred from the supply to the exhaust, like I said, through these common headers for liquid and the vapor line. On year-round, we can go in a horizontal separation up to 40 equivalent feet, and that has to count in bins and that as well. There is no vertical separation, so you have to be level. Again, the max single coil height is 30 inches, and the max length is 155 inches. And this just shows it all in the same plane as well. Typical performance on these types of systems is in the 40% effectiveness, and all those selections and drawings would need to come from heat pipe personnel. Couple of factors. We usually do these in multiples of 2 rows with leading into one common header. So for every heat pipe that you would have, you'd have 2 rows, one common header for the vapor and liquid line for each section. The air velocities, you typically run 300 to 550 feet per minute. And the reason we do that is because those are horizontal fins. If you did have any moisture or condensation, it could get blown pretty well. Fin density is 9 to 12 fins per inch. Again, tubes are vertical, fins horizontal. We can run galvanized casing or stainless steel. We ship these in 2-row modules. It's all 1/2-inch copper. We can do aluminum fins or copper fins. The refrigerant we use would only be 134, and we can coat these with electrofin or Harrisite coating. Supply and exhaust coils do not exactly have to be the same height, so there is some flexibility. If you've got a little bit less area, typically what I see that as an exhaust. The liquid line would have to be the same, but the vapor could vary. Now, you must account for headers when you're designing this for ductwork or air handler. Typically, those headers total is about 8 to 8.5 inches. So we'll help you size those and let you know exactly when we do the drawings for these, the exact height that needs to be accommodated for when you're designing those type systems. We'll help you with the refrigerant line sizing in between, and we just need to make sure that we've got that equivalent length calculated, so we need to take care of any bends and things like that when we do the calculation of that separation between the 2 heat pipe sections. What we'll provide is we'll supply the supply heat pipe modules for the supply and exhaust. We'll have control valves or control panel, which is an option. We'll do on-site vacuuming, and then we'll do on-site charging as well. What others provide is they would provide the installation of the heat pipe within the duct or air handler, any drain pans into the system, the interconnecting piping in between the systems, any piping or installation support or insulation that needs to go. They'll have to do the installation of the control box and wire it back. And then they'll provide the refrigerant, the pressure testing, and the nitrogen for the pressure testing as well. One key thing is we must follow the instructions on piping. We have a design guide for HRM-Vs, which shows you how these need to have to be piped to make sure we have no liquid traps or vapor traps. The other thing is if we have this is in counterflow, but in this scenario, we've got it running in parallel flow, and it shows you how to pipe it in between so you get a counterflow design, which is the optimal design for this type system. We have modulating valves in a NEMA 12 enclosure, which are available. What this would, it would allow you to control it from the BAS system. So if you needed to go in economizer, or if it's on a frosting condition, we would control the flow through the liquid line. Here's an example of a HRM-V in Maryland, 32,000 CFM in the summer, 47 in the winter. Saves about 6.3 million BTUs per year. If you look at the drawing on the left, you'll see multiple pipes running in this direction, and then there's two sets of pipes running off on either side. What this is actually got two exhaust and one common supply. So it's a little bit of a variant on the system, which allows us to do things most energy recovery systems can't do. This is another example in Florida, 30,000 CFM, almost 800,000 BTUs saved per year. Most of these systems that I've seen, typically what they've done is they've used lab exhaust fans. They'll put the exhaust coil in the lab exhaust, near the lab exhaust fans, and then have another dedicated outside air unit with the supply coil, so you get able to do energy recovery in most of those environments. Before I forget, I'll answer any questions at the end, and I'll meet those and answer those in a little bit. Now, one other thing I want to touch on briefly is AHR Guideline 5. It discusses efficiency, which is what we call RER, versus effectiveness. Most energy recovery devices are judged on their effectiveness, how well they actually transfer the heat versus the maximum it could. It says nothing about pressure drop or anything like that. What RER does, it links effectiveness and pressure drop. So two things could have the same effectiveness but different RER. What this guideline is looking at doing, it's looking at taking into consideration any pressure drop, any pumps, motors, purge loss, and air leaks. And it's defined as net conditioned energy recovered divided by the power consumed. This metric is something new that's going to take effect probably within the next year. It's designed for the owner or for energy conscious users. It's saying, yes, I went and recovered that energy, but how much did it cost me to go get that energy? And so we did a quick analysis of a 6-row energy recovery heat pipe. This was done in St. Louis, 10,000 CFM system. We looked at a heat pipe, a standard wheel, which is a plastic wheel. It's about 1.5 inch depth. We looked at a premium wheel, was an 11-inch deep 3-angstrom molecular sieve wheel. We looked at a fixed plate, and then we looked at a glycol loop. These are the effectiveness of each device. This is the amount of BTUs we recovered per each device. Then we calculated the air pressure drop associated with both supply and exhaust, and those are brought in here together. This is any pumps or motors involved in the system, and then this is how much power it costs to have those, and that includes the air pressure drop. So here's how much energy is recovered. So here's a heat pipe, the wheels, the plate, and the glycol loop. Then this is how much power was required to go get that energy. So here we again have the heat pipe, the little plastic wheel. Then we looked at the recovery efficiency ratio, net energy recovered divided by power required, and we're almost equivalent to an 11-inch deep wheel. The key thing about this metric, it really, the further north you go and the further west, where you don't have quite the latent component, the better this metric looks. Now, one other thing we want to talk about is some regional aspects of heat pipes. There's an HRMO, and it's an over and under heat pipe. It's designed for adjacent air streams, can be unit or duct mounted, and typically it's a single season recovery. I recently did analysis across U.S. and Canada. And in this analysis, I had a return temperature of 75 degrees, 50%. I deducted the hours between 55 and 75 degrees for economizer hours on a 10,000 CFM system. The cost of the end user was $15,000 for the heat pipe running 24/7 operation. And you can see anything above this line had less than 1 year payback on a heat pipe. In this line, in this band, we had less than a 2 year payback. And in this band, we had less than a 3 year payback. This was all done with a single season payback for wintertime recovery only. So you can see all the way down into Oklahoma, Arkansas, Atlanta, Georgia, even, you can get less than a 3 year payback with just using a heat pipe in a single season. I ran this analysis because a lot of air handler manufacturers have over and under units rather than side by side as far as their configurable systems. And it saves a lot of space when you're putting it inside the building as well. I also wanted to touch base on a way to enhance an HRM with evaporative cooling. Evaporative cooling is the most primitive form of cooling. It cools the air through the evaporation of water, typically on the exhaust side. Most of the time we see it only in dry climates, but I've started seeing it creep into more other climates as well. So cooling typically in dry climates, like I said, most of it's done in this A and B region. We ran a scenario in Phoenix, Arizona with 10,000 CFM unit, 500 feet per minute, running 24/7. And in this system, what we did, we added an indirect evap cooler onto the exhaust side. It took our supply temperature, our exhaust temperature from 75 down to 62 degrees. And that related to taking our supply temperature from 84 down to 78, which changed our system effectiveness from 55 now up to 85 degrees. So without evap cooling, this is how much energy we saved, and you can see we had a pretty good increase in savings by adding the evaporative cooling into the mix, a 28% increase in savings. We also did this across the U.S. We looked at Phoenix, Las Vegas, Georgia. You still get about 16, 17% increase even into Memphis. Boulder, Colorado, you're looking about 12%. Within Select Plus, you can run this example, and it'll show you what the results are of an indirect evap cooler added to the exhaust side. Now, we don't provide it, but we can show you what those results would be. Now, are there any questions with the heat pipes? I saw one question. Get up on my screen. If the unit is outdoor unit, the control box is mounted on the outside of the unit, is there... I'm not sure. We don't have a NEMA 3R box as a standard option. That would be something we would have to special order. Typically, it's located within. It's mounted on the exterior of the box, typically on the inside. And like if it's on in outdoor units, typically it's going to be mounted within a vestibule. Any other questions? We'll make this available online. If there's further questions, you can contact me or Drew. Well, I hope this was helpful. And if you have any further questions, please contact us.